Hi guys, my name is Ajit and welcome to my YouTube channel. So today we will be writing machine learning equations for decision tree. So we are in part 19. So for the guys who are new to my channel, I have created all the end-to-end machine learning course. I have included all the machine learning equations so you can view my playlist. So I wanted to continue the playlists. So I thought of including decision tree. In the upcoming video, I will be including for random forest and as a boost. Since these machine learning algorithms were not in the end-to-end course, and I wanted to complete these series of all machine learning equations, so I thought of including this in my playlist. So this playlist will be still be continued, and I will be writing all the machine learning equations and so for all the algorithms like decision tree, XGBoost, random forest, which were not there in Coursera, but I will continue to write all these equations. So let's just start with today's topic, which is writing machine learning equations for decision tree. So in this video, we will discuss what is decision tree and what is entropy, Gini index, and information gain. And we will write all these equations from scratch in Jupyter Notebook. So let's start with what is decision tree. So decision tree is is when we ask questions and then classify the module based on the answer. So here you can see the this is the root node. We say this as root node, and these are the internal node. These are the internal node, and this is the leaf node. Okay, so based on the questions, for example, let's say if a patient have a COVID or not. So based on the two feature, or based on the cough and fever, we determine whether a person has a COVID or not. So what in decision tree, what would be my root node? Root node root node can contain feature like cough, or fever, and based on the answer true and false, yes, we split the data and see whether that person has a COVID or not. So based on the cases of cough or not, we say like 5 out of 5 records to have COVID, 3 doesn't have COVID, right? And then again we do a split until we get the best classification. Like if we able to classify our data correctly based on the output that we get from COVID, let's say COVID data. So so based on the questions and answer, we split our decision tree. So how to make a decision tree will be the first question. So let's go to an example, and I will show you step by step uh, the terminology, what is entropy through these examples. Okay, so I have loaded the iris dataset. So this is the built-in dataset that Python provides. So this is my x and y variable. So I have stored my data in data frame, also in numpy array. So in df.head, if you do, you will see your data. So iris data has sepal length, sepal width, petal length, petal width, right? And we have also stored the information in numpy array. So if you look here, so I have stored all this information in numpy array even. Okay, so now let's visualize this information and see you what sort of data we have, or we can group that data in particular cluster or not. So let's visualize my petal length and petal width first. So my data is stored in data frame df. So I will be using sns dot mm, sns dot lmplot, and my data frame is df, comma. So xa will be equals to petal width comma y will be equals to, say, I will take petal length, okay, and actually will be a label, and I will do, let's run this first. So here you can see your regression line. I don't need a regression line here. Let's do fit underscore reg equals false. Okay, so it's fit underscore reg. So you can see this data here. Okay, so in this data set, what you can say, if you draw a line here, if you draw a line here, you can say the data below this line in and data after this line. Okay, let's say, so in data below this line we don't see any classification, because you will not classify your labels, because you only have one label, which is 0, right? So you don't need to classify anything. So this would be your root node. Okay, so this would be your root node. On the right you can see you need to classify your two labels. One would be the, it's on basis of 1 and 2. So we have two labels here. So here we need to do the split of our data, right? But in the left side we don't need to do any split. Okay, so if we don't need to do any split, here the randomness is 0, because we don't need to do any split. Here this is the left part, let's say, and this is the right part. Okay, so in the right part your randomness is high, because randomness is randomness is high because you need to do a split on basis of 1 and 2, 1 or 2. But in the left you don't need to do a split. So what does entropy says? Entropy measures, it measures the randomness in the data. Okay, so here you can see on the left, so on the left, which means data below, say, let's say this is 0.8. So data below 0.8, there is no randomness, because we have already classified no randomness, because we have only one class, and that is already classified. So we don't see any randomness below 0.8 here. But data after, so here my entropy will be 0. Okay, and data after 0.8, we see maximum randomness, we see maximum randomness here after 0.8. So here my entropy will range from, entropy will be greater than 0, right? And my entropy value ranges from 0 to 1, which here 0 means no randomness and 1 means randomness, or maximum randomness, you can say. So the randomness is also known as the impurities. impurities So here we don't see any impurities on the left below 0.8. No impurities, because we have already classified it as one level. And above 0.8 we see maximum impurities, right? So this is what the entropy means. Okay, so what does entropy means? Entropy means randomness in the data, and its value ranges from randomness or impurities in the data. So, and its value ranges from 0 to 1. 0 means no impurities, or randomness, and one means maximum impurities, or randomness. Okay, so we let's check whether this condition holds true or not. So we will write, so this is the formula for calculating entropy, pi times log of pi, and we need to take the sum where the p is your probability, okay, log base 2 of pi. So we will write these equations and we will check whether the condition, whether the split holds true or not for below 0.8 and above 0.8. Okay, so let's say if we draw a line here, sns dot v lines bracket x is equals to 0.8 comma, so y min is equals to 1 and y max is equals to 7. So it's plt ss. So you can see here I have drawn a line. So anything that is below 0.8, we don't see any randomness. Anything that is above 0.8, we see randomness, right? So let's split this data. So whatever there is and there is below 0.8, we will say this as data below, and whatever we have value above 0.8, we will say that as data above. Okay, so let's say I have split underscore columns, uh, split underscore columns equals, so here in this data we have stored this as numpy array. Okay, so here will numpy array will have value in rows and columns. I need all rows, but I need third column because third column has your first, second, third has your pedal width. Okay, so let's say my split columns is on the basis of third column. Okay, so when I choose third column, this will give me pedal width 0.2, so on, 0 1 2 3 pedal width 0.2 and so on. So I want to split my data on the basis of pedal width. So data, let's say data underscore below is equals to, let's say here, less than 0.8 will reside in data below, and let's say the data above greater than 0.8, less than or equals to 0.8. Now if you see actual data below, you will have value less than 0.8, and data above has value greater than 0.8. So I have done this so that I can split my data basis of, so that I can split and check the entropy. Okay, so let's add this in a function. So let's create a function and add all this inside a function. So split data comma split underscore volume, also give split underscore position. Let's give position. We can say split underscore value. So I will keep this. So here 3 will be my split underscore value. 3 will be my column, sorry. And then I need to copy this. So my value will be here, there, and I will return data below data of, okay. Now if we see split data, we'll have data comma column. Split column will be on the basis of 3, which is petal width, and value is 0.8, and I will store that information in above and below. So I did nothing, guys. So simply I created a function and I included all this information inside a function, so that in every time, instead of using petal width, if I want to use another column, I can simply change that here. I can simply change this threshold, the split value here. So for that, I have created a function. So let's check if this is working or not. So should have anything that is below will have this value, okay? Anything here above will have this value. So this looks fine. So now what we will do, we will check our entropy. So like I said, anything below 0.8 will have 0 entropy because we don't see any randomness. We don't have any split value here. Above 0.8 we see the randomness because we can split the value. Also the randomness is considered as impurities, non-randomness, no impurities. Okay, the thing is clear now. Now we will write this equation. So here your P is your probability. Okay, so for entropy, so if you look at data, so your value, so 0, 1 and 2 is, so 0, 1 and 2 says your uh, whether you have, whether you can, 0, 1 and 2 gives you the prediction, like unique. If you look at prediction of your petal width based on the fourth feature, it gives you the prediction 0, 1 or 2. Okay, so I need to see the count of how many counts of we have for 0, how many count is there for 1, and how many count is there for 2. For that we use return underscore counts, that is equals to true. Okay, so this will give me the count. So right now I only need the count so that I can calculate probability. Okay, so for that I will use 1. 1 will give me this value, 0 will give me this value. Okay, so 1 will give me this value. If I choose here 0, it will give me first value, but I need 1 so that I can calculate the probability. So now, so probability will be this value divided by sum of total, right? So let's say if I store this information in counts, so what would be my probability? Probability will be probability pi. This pi, I'm calculating this pi, counts divided by total, np dot count divided by total, counts dot sum. Okay. Now if we look at probability, you can see we got the probability of 33% for all our three values. So these are our dependent variable. So now I need to calculate entropy. So my entropy will be probability times minus np dot log of base 2 of probability, right? And here we see this sign, this means sum. So I'm going to take sum. Okay, so this gives me the probability. Okay, so now I will write this inside a function. So calculate underscore entropy bracket data. So my label columns will be, so I will be taking last column. Okay, I will be using count. So count of this label name, it equals true. Now then probability. So I simply added all the information inside a function, guys. So let's run this. Yeah. Okay. Now if we check our entropy, so here we see data below. Okay. If you look at the entropy for data below, mm, so one thing, I did a mistake because I need the complete data set so that I can retrieve the last column. So I need to use here data. So yeah, so this is the data that contains all the value that is less than 0.8. So why I need to deconvert this? Because I am using here -1, so that -1 will retrieve on the last column, last field, right? So for that, I need to convert this inside the data that contains all the values that is less than 0.8. Okay. So now if we see here entropy for less than, so here if you look your entropy for data all below, so you see here your entropy is 0. Like I said, so anything that is below 0.8, your entropy will be 0 because you don't need anything to split here. So your entropy is 0, randomness is 0, right? So if you look at data above 0.8, above 0.8, and you see your entropy is 1. Okay, so this is the maximum entropy you will have, and your probability is 0.5. Okay, so what we can conclude is, so here what we can conclude, so at probability 0.5, so 0.5 you will have maximum entropy. So if you do a plot here at 0.5, you'll have maximum entropy, right? So at 1, your entropy is 0. Entropy is 0. This point is 0, right? So it follows this curve where at 0.5 you will have maximum entropy, right? That's what we have shown here. So the next one is Gini index, right? So Gini index and entropy works the same. It determines your randomness in the data. Okay. So either we use entropy or Gini index, both are same, but we will come back to the difference of which one should we choose, whether we should choose entropy or Gini index. We will come back later in this video. Okay. So let's first write Gini equation for Gini index, and then we will come back to which one should we choose. Either we should choose entropy or Gini index. Okay. So for Gini index, even if the thing works similar to, but we have slight changes in the formula here. You can see. So your label will be same, count will be same, probability will be same, but your calculation of Gini index will be different here. So Gini, if you convert to Gini, will be, this will be 1 minus 1 minus the probability whole square comma probability whole square, and we need to take the sum, np dot sum. Okay, we need to do axis equals 1 so that we can take the sum row wise. Okay, Gini index. Okay, so this is the formula for calculating Gini index. So let's include this inside a function. Index bracket data. Here even we will return Gini index and probability. Okay. Now let's check Gini index for data below and above, and we will see the difference, okay, of using Gini index. So for data below index, so for data below, your Gini index will be 0 and probability will also be equals to 1. But the changes you will see here for data above. If you go to data above, if you run this, you can see here the Gini index is 0.5 and your probability is 0.5. So what we can conclude is, by using your Gini index, your probability will be at 0.5. You will have maximum Gini index as 0.5. Okay. So here this point is 0.5. Okay, so by using entropy, your value ranges from maximum value ranges from 1. By using Gini index, your maximum value ranges from uh, maximum value is till 0.5. You will have maximum value. For entropy, your maximum value will be 1. So for entropy, your difference will be where maximum value is 1 at probability equals 0.5. Okay, so this is one of the major difference. Your maximum for Gini index, your maximum value is 0.5 at probability 0.5. So this is one of the major difference between entropy and Gini index. Also, the in entropy you need to use log. So this is computationally expensive because we need to use log, expensive. So in here in Gini index, in most of the cases we use Gini index. Most cases is we use Gini Gini index because we don't need to do any computational work like taking log and all. So in most of the machine learning work, we generally prefer using Gini index X in comparison to entropy. Okay, so this too is one of the major difference between entropy and Gini index, which I have shown you. So now moving to information gain. So information gain, what is information gain? So like we need to determine COVID cases, let's say for example, and we have two features, cough and fever. So which one would be my root node so that I can split my data? Okay, so it can be either cough or can be either fever. That will tell me my root node so that I can split my data. Okay, so information gain helps us to decide which feature to use to split our data, whether we should use cough or we should use fever to split our data so that we can predict COVID cases. Okay, so information gain helps us to decide which feature to use to split our data. So whether we should use cough or fever so that we can split our data and can determine COVID cases. Okay, so information gain we can use either through entropy, okay, or through Gini index. So information gain works in both cases. If we use entropy, we calculate information gain. So either we can use Gini index and we can calculate information gain. Okay, so let's consider this as an example. So here this is the dependent variable, which is what we need to predict. This is my dependent variable, and this is my feature. So based on this feature, I need to predict whether whether person have a COVID or not. So what is the formula? So prior entropy minus the sum of probability times new entropy. So what is prior entropy? So prior entropy is so prior entropy is for example, so if we need to determine the COVID cases here, your prior entropy will be the COVID cases. So entropy of COVID cases minus the entropy of either cough or fever. Okay, so let's calculate this one by one. So for prior entropy, so this is your formula. So prior entropy means your output COVID cases, how many COVID cases you have. Okay, so here you can see here three normal cases, 3 by 1 2 3 4 5, 3 by 5 log base 2, 3 by 5 plus not infected cases 2, 2 by 5 log base of this log base of 2 by 5. Okay, so here it's 3 by it's 3 by 2. Okay, let's keep this as 3 by 2. Okay, so this is your formula. So let's calculate this formula. Use this formula to calculate prior entropy first. Okay, so your prior underscore entropy will be equals to, we will use lambda of x comma y, because we need, so we have two output here, normal and effective. So x comma y, so first is 3 by 5. 3 means you want variable here. Okay, so it means x by total 3 by 5. 3 means one variable, 1 2 3 normal, and out of total 5. Total means x plus y, times np dot log 2 of this x divided by x plus y. Okay, this is minus here, minus. So this formula is, you have here minus here. This is minus, again minus. Now we need to take y divided by x plus y here given y. Okay, so this is my prior entropy. So let's check prior entropy for 3 comma 3 3 normal, 2 infected, 3 comma 2, 2 comma 3 or 2 normal, 3 infected is 0.08. So this does not look good. Here two, we have 2 minus, not 2 minus, we have 1 minus. So 0.97. Okay, so by using this formula we get our entropy as 0.97. Okay, so to reiterate what we did, x divided by x plus y. So x here is 2 comma 3, 2 comma 3. So two infected cases. Okay, so 2 by 5 log of 2 by 5, log of 2 by 5 minus 3 by 5. So this is minus. Okay, minus 3 by 5, y of 3 by 5, y is my 3, and total x plus y is 5. So this gives me prior entropy. Okay, so likewise for calculating prior Gini index. So why we are doing this? To calculate information gain. So why we need information gain? So that we can decide which feature to use. Either we should use cough or fever. Okay. So now for prior Gini index. So this is prior Gini index. So let's write formula for prior Gini index. Yeah, prior underscore Gini index equals lambda of x comma y. So for this example, this particular example, I'm just using lambda. So I'm not using iris dataset. Just I'm using this example so that I can explain you how we calculate Gini index. Okay. So what's the math behind calculating Gini index and entropy? So this will be x divided by x plus y, x divided by x plus y whole square plus y divided by y divided by x plus y whole square. Okay, whole square plus closing is correct. Okay, now let's check Gini index for 2 comma 3. Okay, so prior will always be your dependent variable, what you are trying to predict. Okay, so I'm trying to predict COVID cases here. So prior will always be my. So you can see here by using entropy, your value is 0.97, and by using Gini index, your value is 0.848. Okay, so we can see it's like 50% reduction, you can say. So after doing that, what do? We calculate information gain. So now we have prior. Now we know prior entropy and prior information gain. Okay. So now to determine curve. So to determine curve of no cases, no and being normal. How many we have? So two no and normal is only one. Okay. And two no and infected is only one. So here you can see one. For yes, two yes, and your infected is 3s, 1 to 3 yes, and your normal is 2. Okay, so your yes 2. For 3s, your infected is 1, so 1. So information gain will be on the basis of these COVID cases. So COVID cases for cough, your information gain will be probability of no times entropy of. So we are calculating this part. Okay, this part. Okay, so probability of no times entropy of 1 comma 1 1 comma 1 plus probability of yes times entropy of 2 comma 1. Okay, so probability of no will be 1 plus 1 2 2 times 5, because total 5 record we have. Okay, times entropy of 1 by 1 plus probability of s will be 3 times total record 5 and entropy of 2 comma 1. Okay, so we have calculated entropy here. So let's use this formula. So we can say this as result equals, so this is 2 by 5 times, so prior entropy or entropy. Right now we are changing the parameter, that's why. So 2 by 5 entropy will be 1 comma 1 1 comma 1 plus 5 3 by 5 3 by 5 entropy is 2 comma 1 2 comma 1. Okay, so this gives me the result. Okay, so now my final information gain will be equals to prior entropy, which is this. trial entropy minus result. This will be my this will be your final entropy, final information gain. So your information gain is 0.11, 0.01. So this information gain is on the basis of cough, right? So we have taken cough as our feature, cough. So we got information gain on the basis of cough. So likewise, we can do the similar thing for Gini, trial Gini index. Gini index, Gini index. Okay, we can calculate the trial Gini index minus result. Okay, okay, so this. Okay, let me close. So this was on the basis of entropy. So entropy. Just to make things clear, I'm writing this down. And then this was on the basis of Gini index. Okay, let's see. So it's similar. So now we will check. So this is the entropy for cough. This is the information Gini index for cough. Okay. Now we will calculate the entropy for fever. Okay. For fever. So what would be your entropy for fever? Entropy for fever will be, so in fever you can say no normal is 2, no infected is 0. You can say no and infected is 0. Yes, 1, 2, 3. Yes, your infected cases is 1 and normal cases is true. So in terms of fever will be your no, total no is 2 divided by 5 times entropy of 2 comma 0, 2 comma 0, 2 comma 0 plus of yes is 3 by 5. So entropy of 1 comma 2. So let's calculate this. So your result will be 2 by 5 times entropy of 2 comma 0, 2 comma 0, 3 by 5 entropy of 1 comma 2, 1 comma 2, and this one is for fever. Okay, so we are getting this value, this error, because one term is you are taking log. That's why if you look here, if you run this, you are getting error because this term is taking log. So your result will be this value, this value. So your result is 0.55. Okay, so now we need to do subtract with trial entropy, which is 2 comma 3 minus result. So this is for fever. Here we can see the information gain for fever is 0.41. Okay, so let's calculate the Gini index. Gini index for fever. We use the same formula. and Gini index will be 2 comma 0. Okay, here 2 comma 0, and this is 1 comma 1 comma 2. Okay, this is see information gain is 0.21, it's half, so this looks good. So here what we can say, the highest information gain is, so we have received highest information gain from cough, okay, from fever, sorry. So the one that has highest information gain, we will choose that as our first feature. So highest information gain will be our feature. First will be our first feature to split data in decision tree. Okay, so which in our case is, in this example is of is fever, sorry, fever. So here we will choose as our first node will be fever, and then we will do split. Okay, so guys, this was the video that I have explained about entropy, Gini index, the differences between Gini index and entropy, information gain. And in the next video, we will create our decision tree, and we will implement the decision tree in this data set. So hope you like my video. Please subscribe and like my channel and encourage me to create more video. Or thank you so much.